You found a new Aero terminology video from the Ultralight Airplane Workshop. This video is part of a series of videos talking about terminology that's used in aerodynamics. And these are used as a supplement to some of the design videos. That way I don't have to go through a long explanation for a term that I'm using in the design video. I can actually refer viewers back to these videos. Now, I've used the term interference drag on a number of videos, but really didn't go into explaining what it is. So in this video, we're going to talk about interference drag. Let's get to it. The definition of interference drag, or trying to describe what interference drag is sometimes a little bit difficult. We're going to take our cue from Horner's book on fluid dynamic drag, and interference drag is talked about in section 8 of that book. So he says in the introduction of section 8 that interference drag is the extra drag that occurs between the surfaces of two bodies that are either intersecting or they're close to each other. Now, it doesn't have to be extra drag. It can actually be reduced drag also. So what he's talking about is comparing the drag of one body that's by itself in free air, the drag of a second body that's by itself in free air. Now, if you add those two together and they're pretty far apart, you get a total amount of drag, some drag X, let's call it. But then if you put those bodies close to each other or even touching each other, then if you look at that total drag, it will usually be different than the added drags of the independent bodies, that X value. And that difference in drag is what's called the interference drag. So if you take D1 and D2, the independent body drags, and then add the interference drag, you get the total drag of the two bodies when they're close to intersecting or near each other. Now, this doesn't have to be a plus number. A plus number means that the interference drag adds more than the two bodies by themselves are. But you can also get a negative number, which means that you'll actually have less drag when they're near or intersecting than the two bodies separated added together. Now, to help us apply that definition to actual locations on the airplane, we're going to talk about several different instances of where interference drag can occur. For example, tandem bodies. So it'd be one body in front of the other in reference to the airflow direction. So we'll talk about cylinders, one after the other, and then we'll talk about streamlined struts where one is in front of the other. And we'll also talk about intersecting struts. So it might be something like a jury strut intersecting a main strut. We'll also talk about intersections on the tail of an airplane. So that might be the vertical tail intersecting fuselage or horizontal tail intersecting vertical tail, things like that. We'll also talk about how interference drag can occur with right angles, and that's a subset of these tail surface intersections. And it also is directly related to the wing body intersections. So we'll talk about those also. Let's talk about one of the simplified situations, and that's when you have one cylinder in front of another. In this case, cylinders would be something like the struts on an ultralight airplane. A lot of ultralight airplanes use round tubing for the struts. And down near the fuselage, you've got one strut fairly close in front of another strut, pretty much in line with the airflow. And then as you get out closer and closer to the wing, they get farther and farther apart. Well, that would be a really good situation to look at for drag. Now, I've borrowed a lot of the graphs in this presentation from Horner's book. And so if you look in there, you'll see these graphs. Now, what we're going to talk about right now is a Reynolds number of 500,000, if I remember correctly. If you don't know what Reynolds number is, or you don't remember, I'll put a link up here in the upper right-hand corner that you can click that will take you to another aerodynamics terminology video that'll tell you all about Reynolds number. So keep in mind that the drag behind a cylinder changes quite a bit based on the Reynolds number. So in this particular case, at around 500,000, you're typically going to get a vortex above and below a cylinder. So it's not going to be alternating one to the other. It's not going to be laminar, and it's not going to be just plainly turbulent. So at this Reynolds number, you're going to have one above and one below. So at different Reynolds numbers, you're going to have different drag values than what we're going to talk about here, but this is really a pretty good representation. Now for a cylinder by itself, at this Reynolds number, the coefficient of drag is typically about 1.17, and you'll see some documents round up to 1.2. So that's good enough for what we're talking about here. Let's go over here and look at this graph here. On this vertical axis, we have coefficient of drag, And again, if you forget what coefficient drag is, I'll put a link up here in the upper right hand corner so you can go look at another Aero terminology video to refresh yourself on what coefficient of drag is. And then here on the horizontal axis, we have a ratio of the distance between the cylinders divided by the diameter of the cylinders. So for example, on this 4 here, that means this distance here is 4 times what this diameter is. Pretty simple. Well, let's look at the drag on this front cylinder when we have these two cylinders together in the airflow. Now out here where the cylinders are fairly far apart, you can see that this value is about 1.17. That means the drag on this front cylinder, when it's fairly far in front of this rear cylinder, is about the same as a free air measurement. It's almost like it doesn't even know that this rear cylinder is here. But that changes a little bit when they start getting closer together. So when you get down here close to a value of 2, where this distance is twice the diameter, you can actually see there's a fairly significant dip. So this rear cylinder is getting into this vortex setup and disturbing it, and it's actually helping reduce the drag on this front cylinder. But then, of course, as they get closer and closer together, the drag starts going back up again. It just doesn't get quite as high as the free air cylinder. Now let's look at the drag on the rear cylinder. Well, that's way, way down here. It's like 0.3. So the drag on this rear cylinder, regardless of how far apart they are, at least up to around this 9 area, the drag on the rear cylinder is way less than on the front cylinder. Well, that means the total drag of this system, the drag on the front and the drag on the rear, is going to be less than if it was 2 cylinders that were far, far apart. So that means that the drag on an ultralight, where one round tube strut is in front of another, and down near the fuselage, you actually have reduced drag down in that area. So that's kind of neat. So that means it's fairly beneficial to use your round tube struts. Now we're not actually going to compare round tube directly to teardrop shaped tube, because I imagine that the teardrop shaped tube would actually be better. But you're not paying a huge penalty down near the fuselage where you're using these round tube struts. And again, when they get close together down around 2, and then when they're almost touching, this rear tube is actually being pulled forward. It has no drag. It's actually being pushed forward toward the front tube. Now, something that they don't show here in this graph, just because it would be difficult to do, is that as these cylinders get farther and farther apart, this line here for the rear tube starts lifting up higher and higher and higher until it approaches the drag for a cylinder by itself in the airstream. But it happens quite a ways out. So this is a form of interference drag, where you have one object in front of another, and because they're fairly close together, the drag between the two is different than the drag of the two summed together if they were independent. In this case, the interference drag is actually reduced, whereas in most cases, interference drag is an increase in the total drag. Okay, now we're going to look at something very similar, except this time it's going to be streamlined struts. Now this ratio is just a little bit different. Instead of looking at the distance from trailing edge of one to leading edge of the other, it's leading edge to leading edge, that's the X, and instead of diameter, we're looking at the chord of the strut. So that's what this ratio now means down here. So it's just slightly different, but you can think of it the same, at least for our purposes. Now in this case, Reynolds number is 400,000, and we can look at the drag on the two struts. Now in this case, things are a little bit flipped around. Remember before, the front strut had more drag than the rear strut. In this case, it's the opposite. The front strut has less drag than the rear struts. Now this dashed line here is the drag for one strut when it's by itself in the airflow. So if they're at least 3x apart, so the distance from leading edge to leading edge is 3 times the chord of one of these struts, it's just a little bit less than the free flow. So there's just slightly reduced drag on this front strut. But look at the rear strut. Instead of having reduced drag on the rear strut like we did for the cylinders, we actually have more drag on the rear strut. Now here you can see interference drag is actually adding more drag when you add the two together. We're very close to the free flow from the front strut, and we're more on the rear strut. So if you add these two together, it's going to be more than twice the free flow. So instead of having reduced drag, like we do on the cylinders, we have a little bit of extra drag from interference drag on these streamlined struts. Now here's another way of looking at basically the same information. Now instead of from Horner's book, this is from NACA Technical Report 468, which is where Horner got a lot of his information. And the graph is slightly different in this case. Now, the ratio down here on this horizontal axis, still the same thing. The x is leading edge, divided by the diameter instead of the chord. Now, they're not using Reynolds numbers here. They're taking 3 different diameters of strut and they're giving you the airspeed. So you could actually calculate what the Reynolds number is if you want to. But here on the vertical axis, things are just a little bit different. Now here they're talking about difference in drag from the free stream drag. So they're doing that for the rear strut and the front strut. So in this case, this 0 line is the free stream drag, and these lines are how much different those struts are from the free stream drag. So it's a little bit different representation, but it means the same thing. Now this line here is summing these two together. And so we can find out how much difference there is between the combined system drag from what the free stream drag would be. So down here on this ratio, you're going to get at about 4 1/4, you're going to get the maximum amount of drag on your struts. Now it's not a whole lot, it's only about 0.04 more than the free stream drag would be. And then as the struts get farther and farther apart, you start to approach what the free stream drag would be, just like on the cylinders. I have another graph here from that NACA report, report 468, that's kind of nice. Now since up here in this graph, we see that the drag is more for 2 streamlined struts where one is in front of the other, it might be nice to try to reduce that drag just a little bit. We don't really want to have more drag if we can avoid it. So the NACA report looked at what you can do to try to reduce that drag. So one method that would be very simple is just to stick a sheet on the top and the bottom of these 2 tandem struts. Let's compare that to no modification at all, and then let's look at sheets in some of it a teardrop shape and see what that drag is. So that's what these 3 graphs are here. So this A graph is the original, so it's basically, it looks like this line, except the scale is a little bit higher here in the height, but it's the same exact shape. Now what if you stick a sheet on the top and a sheet on the bottom, just kind of bridge that top and bottom gaps on these 2 struts? Well, that's kind of interesting. So at least for this ratio of about 3 up to 10, you actually have less drag than doing nothing. So that's kind of nice. But after you get up to that ratio of about 10, then the drag starts increasing. So if your diameter, and on these struts, diameter is basically the thickness of the strut. So if your diameter is 1/10 of the distance between them, let's say you had a 1.2 inch diameter, then up to a distance of about 1 foot, you could put sheet on the top and bottom and reduce the drag on these struts. Well, that's not much of a separation. That only takes care of maybe a foot from the fuselage out onto the struts, maybe just a little bit more. So let's look at something better. Now, something better would be to bend these sheets into a teardrop shape around these struts. In this case, they're showing round struts instead of teardrop shaped struts, which makes sense if it's completely buried inside. What's the use of doing a teardrop shaped strut? But that's this C line here, and you can see that is a whole lot less drag down here. So even though we end up being a little bit thicker than either of these teardrop streamlined struts, we have way, way less drag. I mean, in this area, it's roughly a factor of 2. We have nearly half the drag of the individual struts together, and that extends out quite a ways. Now, they're assuming a line right in here. They didn't go ahead and measure this, it looks like. But out to at least a factor of 12 ratio, you have either equal or less than drag than if you had the individual struts. So you can at least reduce your drag a little bit on your struts by these various operations. Here's another picture from Horner's book. In this case, we're looking at a situation where a strut is angled to a surface. Now, example that would be on the tail of an airplane that has horizontal and vertical stabilizers, and you've got a strut going from the top surface of the horizontal stabilizer up to the side of the vertical stabilizer, connecting them together, making them a little stiffer. And generally, that tube or streamlined strut is going to be at a slight angle to that top surface of the horizontal tail. And also, it'll be angled into the side of the vertical tail too. But let's talk about what interference drag is like in this kind of situation. Now you're going to get interference drag where that strut comes down and intersects with the top of that horizontal tail. Now that angle from vertical is called beta. I know it's a little bit blurry here, but they're calling that beta. We got the thickness of the strut, that's T right here. and the intersection down here, where the boundary layer of the top of the horizontal tail and the boundary layer on the strut are going to intersect, and we're going to get some interference drag. And so this diagram over here talks about what's going to happen as that angle changes. So down here on the horizontal, this is the angle beta. So 0 would be straight up and down. And as we increase here, we're leaning it more and more to the right. And up here on the vertical axis, this is coefficient of drag. Now down here in this little area here, this is the drag of the individual parts summed together. So the drag of the strut by itself and the drag of the horizontal tail by itself. So that's what this is here. Now this little increment here, this horizontal area, is the interference drag you would have when beta is 0. In other words, the interference drag you would have when this is straight up and down. So above this dotted line then is going to be the change in interference drag as you change this angle. So of course out at here at 0, you just have the interference drag of the two parts. Now as you increase that angle, you're starting to lay it over. You can see from this graph, we're getting more and more interference drag. So when we get up here to about 40 degrees, our interference drag has doubled. So that's pretty significant. So it would be nice if we could find a way to reduce this interference drag if we can, because leaning these struts over really increases it. So another place you're going to have interference drag because of struts is going to be where the strut intersects the wing, because that's a pretty big angle from vertical. That's getting upwards close up here to 60. So we've even more than doubled our interference drag up in this area. So in that spot, that's also a good place to try to reduce our interference drag. So here's another example of interference drag, which is similar to what we were just looking at. In this case, it's two struts that intersect, and we're looking at it head on. So there's a strut here horizontal, strut vertical. And this graph over here, on the horizontal part, we're looking at the thickness of the strut divided by the chord of the strut. So at 0.5, it's half as thick as the chord. So on this vertical part up here, we're only looking at the interference drag. We've subtracted out the section drag of these parts. So this line here is the drag that we get as the part gets thicker and thicker. So we start out at 0 where we just have the sectional drag. And then as a part gets thicker and thicker, our interference drag goes up and up pretty fast. If you can keep your struts fairly thin compared to the chord, you'll have less interference drag. But what this graph is trying to tell us is what happens if you stick a fillet in here between these two struts on this intersection of the struts. What happens then? Now we'd have to dig down into details to find out how big a fillet they're talking about. But with the example that they used, by sticking a fillet in here, we have a nearly linear response, and it's way, way less than the interference drag without a fillet. So if we can find ways to stick a properly sized fillet in here, we can really reduce the interference drag on an intersection like this. Now this also implies then anytime that we have an intersection like this between two parts on an airplane, we have airflow going over them, sticking in a fillet should reduce the interference drag. Now over here on the right hand side, we're actually getting a little bit more into the fillets that they're talking about. Here we're having a rear view instead of a head-on view, and then this is a sectional cutoff view. So again, here's the vertical one, here's the horizontal one, except we're looking at the end of the tube. So here we're looking at various different shapes. This top one, there is no fillet whatsoever, so they're talking about a coefficient of drag of 3.3 for this particular configuration of struts. Now here they stuck in a little bit of a fillet. So you can see it here just a little bit. This is the black area here. You can see that they filleted between the two in the angle, and then they also filleted a little bit aft. And you can see that here. Now in that case, we cut the drag way down, almost in half, just by a little bit of filleting. That's pretty impressive. Now here, they got a little more carried away. They filleted about the same amount in the intersection here, maybe just a little bit more, but they added a whole lot here back on the trailing edge. Not very wide, but fairly long. Now here, the drag went down to 0.5, so that's less than 1/6 of the drag that we had up here. That's really impressive. And then they extended it out just a little bit farther and wider. In that case, we're at 0.2, so we're less than 1/10 of the drag. So by adding a little bit of filleting and adding a little bit more here on the trailing edge, we can really reduce that interference drag. Down here, it's almost insignificant. Now, one of the common places to get interference drag is on the tail of your airplane. Now, this is another picture from Horner's book where they compared various tail arrangements on airplanes to try to figure out how much the tail drag is going to be interference drag. Now, they did not do these tests in wind tunnels. It was done analytically. And what they wanted to find out is what percentage of the interference drag is compared to sectional drag. So it would basically be the drag of the tail ignoring the interference drag. Now, all these tails were calculated to have the same aerodynamic forces applied on the airplane. So they should roughly be aerodynamic equivalent as far as pitch control and directional control. So for a V-tail, they said that the interference drag is going to be about 3% of the sectional drag. Now, where are we going to get that interference drag? So it's going to be on the top and bottom of the tail surfaces where it intersects the fuselage. So we actually have 4 areas where we get interference drag. The top on the left side, top on the right side, bottom on the left side, and bottom on the right side. So that's 4 areas where we can get interference drag. And that's for a V-tail airplane. Now, what about a tail where the horizontal tail is mounted midway on the vertical tail? Now, in that case, it says that the interference drag is going to be 6% of the sectional drag. So that's double what we had for the V-tail. Well, what places do we have interference? The top side of the horizontal vertical tail intersections, so that's 2. The bottom side of the horizontal and vertical tail intersections, that's 2 more. And then also where the vertical tail intersects the fuselage, that's 2 more. So that's 6 compared to 4 over here. Now, what about a more typical tail configuration where the horizontal tail intersects the fuselage and the vertical tail does too? Now, in that case, again, we have 1, 2, 3, 4, 5, 6 intersections. Now, in that case, they said the interference drag is 5% of the sectional drag. Now, that's actually less than this up here where we have the same number of intersections. Now, that's because we're intersecting a rounded surface here on the fuselage for all of our intersections. But up here, we have a sharper intersection, a 90-degree intersection, whereas on the fuselage, it's tapering off rapidly as it comes around the corner. We don't have quite as much interference. So that's why this is a little bit less than this, even though we have the same number of intersections. Let's look here at this arrangement. So it's very similar to this one, except in this case, a horizontal tail is sitting on top the fuselage. We're going to have fewer intersections. We got the 2 on top the horizontal tail where the vertical tail is, and then we only have 2 underneath where horizontal tail is intersecting the fuselage. So in that case, they said the interference is 4% of the sectional drag. So that's only slightly more than this, but it's the same number of intersections, 4 and 4. So again, the reason this one is slightly more is we have sharper intersections here on top, but we have rounded off intersections here underneath. Now let's look at some of the twin tail configurations. Now, as you can probably guess by this point, we have a whole lot more intersections here. We have 4 with the fuselage here in the center, and then we have 4 more, 2 on this side and 2 on this side that are fairly sharp. So you might guess that that's a whole lot more interference drag, and you're right. In this case, it's 8% of the sectional drag. Now again, this one and this one are very similar, except here, again, the horizontal tail is on top of the fuselage, so actually get rid of 2 intersections. So as you would think that this one should be a little bit less than this one, and it is. It goes down to 6% compared to 8. Now, what about these 2? These are very similar, except we don't have the lower part of a vertical surface sticking out underneath the horizontal tail. So we actually get rid of 2 intersections that are underneath the horizontal tail. So that's 2 fewer intersections, and as you might guess, this one has lower interference drag than this one, 4% compared to 6%. And then let's go look at the absolute worst one, and that's this one over here. So we have 4 sharp interference drags over here, another 4 over here, that's 8, and then another 4 here with the fuselage. So that's 12 intersections. So this is really the worst thing to do. So I would avoid this arrangement at all costs if you can. So if your only concern or your highest priority happens to be getting rid of interference drag, then of course your V-tail would be a good solution. But Naturally, lots of other trade-offs come into consideration, so that might not be the best deal. This next one here is a fairly good solution if you want to have a conventional tail. It's only just a little more interference drag. That's not bad at all. And then if for some reason you need to have a dual rudder situation, then this situation here is a little bit better. So it still has 4% compared to this one. And then most of these others, it would be best to avoid them if you can. Now, one that they did not put in here is a T-tail. Here's a picture from Dan Raymer's book, Aircraft Design, A Conceptual Approach. And here's a picture of a T-tail. Up on the horizontal tail, on top of the vertical tail, you're going to have two intersections, and then you'll have two more intersections where the vertical tail intersects the fuselage. So that's only 4 intersections. Now, 2 of those are going to be sharp, and 2 of them are going to be rounded. So I would expect that to have about the same interference drag as this configuration right here, about 4% of the sectional drag. So that's pretty good too. Let's reconsider this configuration over here again. What if we could reduce the interference drag even more? Let's investigate that. So this is a situation that we're talking about where things are flipped over a little bit. So let's call this your vertical surface and this your horizontal surface, and this is the intersection. So just think about this actually being flipped over on top, like here. So you've got a fairly sharp curve here. So we have an example of a measured coefficient of drag of 0.0005. Now what if we stick a fillet in here like we did when we're talking about the strut intersecting with the wing? That should reduce the drag a little bit, and it does. We're down to 0.0004 now. So that's not bad, a 20% reduction in the interference drag. But we can do even more. What if we just completely rounded that intersection like we did here? In that case, we'd knock that interference drag, well, almost to 0. Now they have a couple different results that they came up with. They actually said in this case the interference drag is completely gone, and we actually are just a little bit better at minus 0.0005 or plus 0.001. It kind of depends on a few things, but you can essentially eliminate interference drag by putting a big radius here in your intersection. In this case, they're talking about a radius that is 20% of the chord. So in this case, we're looking head on or rear on into our intersection. So the chord is actually in and out of the page here. So this radius here in the mid part of your airfoil being about 20% of the chord or twice the thickness, either one, and you can pretty much eliminate interference drag. So interference drag can vary depending on where you place your wing against another body. So in this case, it could be a wing attached to the fuselage, a wing attached to a nacelle, and the position of the vertical tail relative to the horizontal tail fore and aft. So that's what we're looking at here. What we're looking at here on the horizontal axis is the placement of this airfoil along the longitudinal axis of this body. So if this dot is clear up here, that's 0. If this dot on this airfoil is moved all the way back here, that's all the way over here on the right hand. So that would be 1. So L is distance from leading edge of this to trailing edge. X is the position along that length. Up here on this vertical axis, we're looking at interference drag. So as you can see, if this airfoil is placed all the way up here where the midpoint of the airfoil is right at the leading edge of this body, our interference drag is almost 0. And if you move it aft to where it's way, way back here, the interference drag is pretty low. It doesn't go down to 0, at least they didn't measure it down to 0, but it goes down pretty low. But if you're right here at about the 55 or 60% area, right in here, your interference drag is going to be at a maximum. So if you can, you want to try to avoid having your wing attached right back in this aft area. Now, of course, most wings on most fuselages are going to be attached probably up in about this area, roughly the 25% area. So you've got a fair amount of interference drag there. Now let's apply a little bit of what we've learned. This is the tail on the UWS-1 Ultralight airplane. Now this is a composite airplane, so it's a little bit easier to do some of what I did here than it would be on an aluminum airplane or even a tube and fabric airplane. Now I don't have the fuselage in here. I just wanted to concentrate out here on this intersection between the horizontal tail and the vertical tail. Now let's take a front view. So here you can see an example of what we were talking about earlier about rounding out the corner between two flying surfaces. So that's what I've done here. So here's your horizontal tail, and at this intersection I put a large radius in here going up to the vertical tail. So we should significantly reduce our interference drag just because of this interface here, this intersection between the horizontal tail and the vertical tail. Now let's take a view from the left. So again, here's the horizontal tail. I'll kind of turn it like this a little bit so you can see the horizontal tail here, and here's the vertical tails. And here you can see an example of what we were talking about when we were talking about mounting a wing to a body. So I've shifted the rudders, the vertical tails, about 50% aft of the horizontal tail. So the thickest part of this horizontal tail is going to be close to the leading edge of this vertical tail, and vice versa. The thickest part of this vertical tail is close to the trailing edge of our horizontal tail. So we should get significantly reduced interference drag by shifting this vertical tail backwards. And just as a point of information, I did not select this twin vertical tail arrangement just to try to reduce the interference drag. I selected this because I'm going to have twin propellers in front, and these vertical tails I wanted to have in the propeller slipstreams so I can have better directional control authority if one of those motors should happen to fail. So I'm actually going to have increased drag because these vertical tails and a portion of the horizontal tail are going to be in that propeller slipstream. So all this half hour we spent talking about interference drag comes down to several things. Anytime you have one aerodynamic surface mate with another one, you want to try to ferret. Now that may be a curve in between the two surfaces, or it could be a straight line, which we really didn't talk about in this video. But even doing a fillet between the two surfaces and filling in that corner a little bit, that will help reduce interference drag. And for a curved one, you really don't need to have this radius be more than about 20% of the chord of your smallest surface. And another thing we just finished talking about is you want to try to avoid having the thickest part of your two curved aerodynamic surfaces be at the same location, because that's roughly where you're going to get your maximum interference drag. You want to move one forward or aft if you can. And one that I didn't talk about here, which is a little harder to deal with, you got to do it early on in the design process, is you want to have as few interference drag locations as possible. And we talked about that on various tail configuration. Well, that's it for this Aero terminology video. Thanks for watching. Until next time.